Imagining I've taken a person and I've removed your entire vascular system at a go. And then you have your heart at one end, the blood comes out and it goes through a fairly thick pipe, your aorta. And then as it goes through the rest of your body, it goes into branches which are smaller and smaller. The individual branches are smaller, but there are more of them. And so it turns out the total area that you have, the total area of the flow is bigger as you go further and further through the vascular system. We want to specifically look at the capillaries. And we're going to solve this problem by looking at continuity. Whenever you have liquid flowing through a tube, and this is something which will be important for us for many things that we're going to see today, we have the following situation. We have liquid flowing through a tube, and I have liquid flowing through a tube of cross-section area A1 here, moving at a speed V1. As it goes through the tube, if the tube narrows, all the fluid that went through here has to go through this area. And so all of it has to squeeze through a smaller area, and as a consequence, it speeds up. Now, we know this. If you drive up the Poudre River, if you look at places where the channel gets narrower, the rate of flow speeds up. Interestingly, when I taught in Ohio, I would ask people, if you have fluid going through a tube and it gets narrower, what happens to the speed? And people would say, it slows down. And I was really puzzled by this, but rivers in Ohio don't really move. It's kind of hard to tell they're going anywhere because it's real flat. And people thought about traffic, and they said, oh, you got 4 lanes, go down to 2 lanes, and everybody stops. Don't think about traffic. Think about the Poudre River here. River, big, wide area, going nice and slow. All of a sudden, all that water has to make it through a narrower spot. The only way that can happen is if the fluid speeds up, and so it's got to be going faster here. On the flip side, if it's going through your blood system, if it's starting in the aorta, it's going pretty fast. As it goes to successive levels of branching, the total area of that branch gets bigger and bigger, and so it slows down. And we know that has to be true because all the blood that goes out of your heart comes back into it, hopefully. You're not losing any. And so we can use continuity for this. So it leaves the aorta, which has this radius at a speed of 0.30 meters per second. In the capillaries, the speed is reduced to 1 millimeter per second. And that's an actual picture of blood moving through a capillary, and the red blood cells are basically going through single file when they get to that point. And the flow is quite slow when it gets to that point. And you want that to be true because you have to have time for the magic of diffusion to take place. So we imagine blood coming out of your aorta, okay? And it's got a certain radius. And when we can calculate the area, that's just pi times r1 squared. It's moving at a certain velocity, v1, which we can calculate, or I'm sorry, which is given. It's given as 0.30 meters per second. How do we know that? Oh yes, we will do a measurement in class of this. And then it branches, but what ends up happening is we're not going to consider the individual branches. We're going to consider the area of all the branches considered together. So the blood comes and it branches. The individual branches are smaller, but the total area of this plus this plus this is bigger. And by the time it gets to your capillaries, you have a whole lot of branches. They're all individually quite small, but the total area of them is quite large. And we want to work out what's the total area of all the capillaries considered together. That's A2. That's A2. Now that's going to be pi times R2 all squared. If I imagine taking all your capillaries and making them into one uber blood vessel, right? One big one, we can work out how big it would have to be. And I know the velocity at this point, that's V2. V2 is 0.001 meters per second. And then I use the continuity equation. V1 times A1 is equal to V2 times A2. And since it's slowing down, we know for a fact that the total area has to be getting bigger. So I have 0.30 meters per second times the area, which is pi times the radius. And we're given the radius as 0.90 centimeters squared. And I'm going to have centimeters on the left side and centimeters on the right side. So I'm going to leave things in centimeters. 0.90 centimeters squared is equal to 0.001 meter per second times pi times the radius r2 squared. And r2 is what we're solving for. And then I have everything I need in this equation except for R2. And if I work that out, I get R2 is 16 centimeters. 16 centimeters is a bit over 6 inches, so the diameter is a bit over a foot. So if you took all the capillaries in your body and bundled them together, and you looked at the inside area, it would make a tube about this big, actually. That's surprising, isn't it? That's really surprising. That's a lot of area. But think about it. They're in every tissue in your body, so you'd have to add them all up. And it's quite a large area. That's one quick issue of fluid flow.